I'm Arjun. I'm one of the founders of Connext. I wish I knew Spanish well enough to give this talk in Spanish next time. This talk is called Building Cross-Chain Applications. It's about bridges, which I know are kind of a scary topic right now, but I'm hoping that over the course of this talk, you'll get to learn a little bit more about the different kinds of bridge constructions that are out there, feel a little bit safer about them, and also explore some of the different ways in which you can use bridges to build really, really new and interesting kinds of applications. So without further ado, background. So I'm going to start by talking a little bit about bridges and about what exactly they are and what makes them special and how they work. So what is a bridge? I don't know where to point this. There we go. Oh. Is there a way to... Oh, there we go. What is a bridge? A bridge is any mechanism where a single chain can communicate with another chain. Basically, a way to think about it is you want to allow a chain to be able to read and understand the state of another chain. The most intuitive way to do this is natively verified bridges. So basically, you run a light client of one chain in another chain. This is the most trustless mechanism to verify the state of another chain. But it also requires doing a lot of additional work. You need to verify consensus, so that means for every new chain you add and you support, you need to build a custom implementation of a light client. On many chains, this isn't even possible. So for instance, we still don't have Ethereum light clients, and the reason for that is that building light clients of Ethereum is actually incredibly difficult. So as a result of that, people have moved to other kinds of bridge constructions lately. One of the key ones that we've seen is externally verified bridges. And this is basically any mechanism for relaying data across chains that relies on some external actor to actually supply the data to the destination chain. So this could be something simple like Coinbase. Right? Coinbase is an externally verified bridge because what they're doing is they're taking in transfers on one chain and then sending them on another chain. And they are custodially responsible for doing that. But it can also be more sophisticated constructions. It could be a multi-sig, as in the case of things like Poly Network, multi-chain, et cetera. Or it could even be a POS chain of its own, as is the case with xChain. Now, the difficulty with externally verified bridges is that you have this external actors. So no matter what happens, you're trusting that multi-sig or that chain or that entity to relay data correctly. And when they don't do that, that leads to hacks or economic attacks that can cause widespread contagion, as we've seen for a lot of the bridges out there. The last kind of bridge construction, and I'll just touch on this one briefly, is locally verified bridges. And this includes things like atomic swaps. In a locally verified bridge, you have a counterparty that you're interacting with and you're swapping funds with in order to do a transaction. Now, the difficulty with locally verified bridges is that they're kind of a special case. You can atomic swap with somebody trustlessly, but you can't really use that mechanism to read data on another chain. And so we don't generally, this kind of falls under the general construction of what we consider bridges as a way to get data or funds across chains. But you're not really getting the funds or data across chains. What you're doing is just swapping with somebody who's on the other side. I realize I jumped really, really deeply into that. But the reason for that is I wanted to show that there is a really interesting trade-off space around bridges. And there tends to always be trade-offs associated with any kind of decentralized infrastructure. And for bridges, there's a trade-off around the three properties of generalizability, which means can this bridge send arbitrary data between chains? Trust minimization, so are you relying on an external multisig or external set of actors to make this transaction happen? Or extensibility, can you take this bridge and copy pasta it to every single chain? Now, about a year ago, we created this mental model to explain the bridge trade-off space. And about 2 months later, it was completely ruined because someone created a new kind of bridge, which is an optimistic bridge. Optimistic bridges are a relatively newer construction where you use fraud proofs to relay data across chains. They work similarly to optimistic rollups. You take some data and you push it from an origin chain to a destination chain. And then similar to an optimistic rollup, you have a certain period of time within which that data is finalized. So within 30 minutes, anyone can dispute the data and prove that fraud occurred. The really cool thing about this is that this is a relatively simple construction. Similar to an optimistic rollup, it can be deployed anywhere. It exists directly inside of the VM. And it has generally very good trust assumptions. But like I mentioned earlier, there are always trade-offs. And the trade-off of optimistic bridges is latency. So any transaction that goes across chains takes 30 minutes to complete. And so unfortunately, we always end up in this kind of shitty situation where no matter what happens, you're giving up something. And if you ever interact with the bridge and they say they are the perfect solution, chances are what they're doing is sacrificing trust. Is there a way out of this? Well, for Ethereum scalability trilemma, what we ended up realizing was that the way that you can beat trade-off spaces in decentralized systems is to have modularity. Basically, split out the different functions of a bridge, so in that way you can achieve the trust minimization properties that you're looking for while giving up the least amount of desirable properties. So this is what Connext does. We are a modular stack for bridging. We work with previously with Nomad, which is an optimistic bridging layer. And generally, this is a model that can work with any kind of optimistic bridge, where we have a network of off-chain actors called routers that fast execute transactions on top of systems that have latency. A good way to think about this is to think about things like hop and across. They have a similar mental model where you're sending a transaction across a roll-up bridge. That transaction takes 7 days to execute on Ethereum. But hop and across short-circuit this by providing fast liquidity for the exit before that 7-day window is up. And the reason that they're able to do this is because off-chain, any off-chain actor can know that fraud has occurred right away. Right? The idea behind an optimistic delay window, so the 7-day window for an optimistic rollup or the 30-minute window for an optimistic bridge, is that you need to give time for some off-chain actor to prove fraud to the chain. But of course, if you're an off-chain actor yourself, you can know right away that that's happened and provide liquidity quickly for an exit. What does this give us? For Connext, this means 2 minutes of latency for normal calls that you would do as a user. So that's unauthenticated calls, which basically means a call to a public function. So if you want to, for instance, call Uniswap on Polygon from your wallet on Arbitrum, that can happen instantly. On the other hand, 30 minutes, the full Nomad or other optimistic bridge latency window for authenticated calls. So that means any call that actually checks the origin of a transaction. So a good example of that is updating the owner of a contract from a DAO contract. So you have your DAO running on Optimism, and you need to update the owners of your contracts running on other chains like Polygon or Gnosis Chain. So what about hacks? One of the biggest things that I think people have seen over the course of the last year or so is that bridges are extremely, extremely dangerous technology. And it's not because they are inherently flawed in any way. In fact, ultimately there is no way for us to scale this ecosystem without some kind of bridges. And rollups kind of fall into this as well. Rollups are really a way to have bidirectional communication to something that kind of looks like a sidechain. But how do we actually build safe bridges? And I think this is really where optimistic bridges shine. The kinds of attacks that exist on bridges and the kinds of hacks that we've seen have always fallen into certain categories, either compromises of the root of trust, so that's like an economic attack where you compromise the keys of a bridge. The Ronin network bridge hack is a good example of this. Or they're implementation bugs. So the Nomad hack that just recently happened is another good example of this. And in both of these cases, using optimistic bridges, using the optimistic watchers that are actually like checking for fraud on each chain can help you catch some of these types of issues and shut bridges down before they actually completely depeg the underlying assets and lead to widespread risk in these ecosystems. I could talk about bridge security for like 2 hours, so I'm going to stop there. But if you have more questions, I'll be happy to chat about it after this talk. So that was a quick rough and ready background on bridges. Why are bridges important? What do they actually let us do? Bridges let us build cross-chain applications. Cross-chain applications are applications that interact with state that lives on multiple chains at the same time. And there's a big benefit to doing this. You don't want to give users this like fragmented experience where where they're interacting with like Aave running on Polygon, and then they have to go switch networks and switch chains to go interact with Aave running on Optimism. That's a really, really shitty UX. As a user, what you actually want is you just want to get the best rate anywhere. Or you want to be able to select a target chain, but be able to deposit into it from any other chain. So how do you do that? What do bridges enable? And how do they actually help us accomplish this? So to start with, I'd like to introduce a primitive that we've created, which is called xCall. xCall is a very, very simple low-level Solidity primitive that allows you to make asynchronous calls across chains. A good way to think about it is to think of the Solidity call method. So for those of you that have written Solidity and built contracts, call is a lower-level function that allows you to pass data to another contract that exists on the same chain and execute whatever is happening on the other side. It's a bit of an unsafe function because you don't really have full transparency into what's going on. So most of the time, people will not use this low-level function. They'll use libraries instead. But you can build on top of that function to do a lot of, that function ends up being the basis of composability on blockchains. xCall does the same thing. It allows you to call contracts on another chain asynchronously, the same way that you call contracts on the same chain. What's a good way to think about this? So those of you that are JavaScript developers, a good mental model for this is how you make asynchronous calls in JavaScript. When you execute something in JavaScript that is accessing a resource that is far away, what you're effectively doing is calling asynchronously to that resource, and then the process halts and waits for that call to execute and come back and execute something else called a callback, basically a function that you specify that does something after you get that data. Similarly, xCall lets you do a remote call to another chain and halts the process, or I guess it doesn't exactly halt, but basically the function terminates on one chain in a single block, calls a contract that lives on another chain asynchronously, and just like JavaScript, lets you come back and execute a callback at some point in the future. Now, of course, this is blockchains, not JavaScript, and so this process takes time and costs money, right? It's not like traditional web development where you can make asynchronous calls to a lot of different places all at once really cheaply and expect them to get back to you within like a couple of seconds. On the other hand, with blockchains, this will typically take, again, at least a couple of minutes of latency and will cost gas. But the core principles are very, very similar. And it even extends to the way that we think about things like gas. So for instance, when you're calling xCall, you pay gas on the origin chain in the origin chain native asset. And similarly to any normal call that you would do on chain, if there isn't enough gas to complete the execution and the execution halts, you can simply bump gas to make sure that it goes through faster. This also happens on the sending chain. What does this look like in practice? What we're trying to do is find a way to emulate the existing Solidity development patterns as much as possible and just introduce only this one simple asynchrony primitive. And so the way that this looks currently is to basically pass a bunch of data into xCall in the same way that you would pass data into call, and then specify a callback that gets executed later. But what we'd like to do is work towards a model where we build libraries, similar to for instance, like the Open Zeppelin wrapper libraries that allow you to call common contracts like Uniswap, where instead of doing iUniswap v2 router.swap, you would do xi Uniswap v2 router instantiate by passing in a chain ID of the target chain, and then .swap, and then .callback. Now that we've gone over the kind of the basics of this idea, let's talk a little bit about Zap design. How do we think about building applications in this asynchronous world, and what kinds of issues do we run into? Building asynchronous applications is not like building synchronous ones. It's actually a lot more similar to building in the traditional distributed systems world, because you have to think about a lot of these really pesky issues that you wouldn't have thought about otherwise. One of those issues is concurrency. So imagine if we're building a cross-chain AMM, and that cross-chain AMM has a pool on a destination chain, so a pool of USDC on Optimism, and you want to allow people to transact from that pool on any other number of chains concurrently. One of the risks that you run into here is that if you have calls, xCalls coming from multiple origin domains, they may be trying to interact with the same liquidity at the same time. So that can lead to either collisions where you have deadlocks where multiple transactions are trying to send funds from the same, basically the same funds at the same time, effectively an attempted double spend, or shitty UX where a user can basically just execute a transaction across chains but then never actually get their funds. And this leads us to all sorts of weird things that we have to think about, where we now have to think about concurrency control, which is not something that we've had to do typically in blockchains because, or at least when building on top of blockchains, because everything executes within a single block. But now you have to think about, okay, well, what happens to this system if you have multiple interactions happening to it at the same time? Some of the strategies that people will end up using will be things like segmentation, fragmenting the liquidity in a single pool, optimistic locking, which is basically serially ordering transactions, pessimistic locking, which is a high overhead communication mechanism where you lock a part of the pool. These are all traditional distributed systems mechanisms for handling concurrency. Now, unfortunately, in the AMM case, none of these options are really that great. And this is one of the challenges, is how will we actually be able to build some of the same user experiences? And as it turns out, we may not be able to do so without sacrificing at least some capital efficiency or some additional gas overhead. Another really, really common pitfall that I see people running into all the time is synchrony assumptions. So a synchrony assumption is the idea that you cannot actually know the state of two chains on a single chain at any given time. To think about this, let's go back to our AMM example again, where we have a pool of USDC sitting on Optimism and a pool of USDC sitting on Arbitrum. And you want to send a transaction similar to any AMM, send a transaction that inserts funds into pool of X and then outputs funds from pool of Y. How do you calculate the fees? How do you calculate the swap rate for that transaction? Well, if you're doing this on chain, you know when you initiate the transaction to the origin chain pool that origin chain pool has a certain state. So say it has 100 million USDC in it. However, by the time that transaction actually goes across the bridge, and this is regardless of whether that takes a couple of minutes, 30 minutes, 10 seconds, even 1 second, by the time that transaction goes across the bridge, the pool state that you have on the destination chain is now different from the actual pool state on the origin chain. And that's because there is always a time window between these two things. So if you think about the fundamental mathematics of why of AMMs and why we think about AMMs as this constant function, when you have a system where you have a synchrony assumption, you now have a little bit of a weird situation where you don't actually have a constant product in your AM at all. And this is obviously quite dangerous. It means that miners can run your AMM transactions. It means it is possible for people to even rug all of the funds. And so what that means is that this, ultimately, this construction that we have for AMMs is actually vulnerable to huge problems when you try to build the same kind of core AMM, like one pool on every chain construction in a multi-chain world. TLDR, building cross-chain applications is tough. There's a lot of really, really interesting things you can do, but it's also kind of messy. And I think a lot of the reasons why it's tough is because not only are you dealing with these applications now as a distributed system, so as a system that has state on multiple chains that you have to manage and concurrency on those chains, but you also have some of these trade-offs. Messaging overhead is costly. So like when you are, if you are a developer building a traditional web application that is storing a bunch of data across a bunch of databases, syncing those databases doesn't cost a lot of money. Whereas on Ethereum, syncing your state across multiple chains costs gas every single time. Authenticated calls also have latency. So that means that it can take up to 30 minutes to actually do any intensive call that requires knowing where that call came from. And most importantly, state updating matters. So MEV is a thing that exists, and it's only extremely magnified in a cross-chain world. And as we've seen from this curve, getting it wrong means there are now massive vulnerabilities that exist inside of your protocol. But there are also a lot of really interesting things you can build. And I think that this is really where we've seen a lot of folks starting to explore and play with these ideas. And of course, people are running into some of the pitfalls of building cross-chain applications. But there is also a bunch of completely innovative use cases that are coming out of this model that a lot of people haven't really thought of before. So some good examples are Superfluid. Superfluid is building cross-chain money streaming. So at the simplest level, that is setting up streams on Superfluid on one chain that can then be withdrawn on another chain. But even more complex, you can do really interesting things like cross-chain DAO payouts, so liquidity mining campaigns and things like that that happen across chains with a DAO existing on one chain and the campaigns happening across multiple different ecosystems at once. And of course, a lot of other really, really interesting use cases for money streaming that still have yet to be discovered. Another good project that we've been working closely with is Keeper. And we've been working with the DeFi Wonderland team on helping take Keeper multi-chain. And a big piece of this is bringing Uni v3 TWAPs to every chain. Right? So the big benefit of TWAP oracles is to not necessarily need an external oracle. So you minimize the external trust on something like Chainlink by using on-chain pricing data for whatever it is that you're building. But of course, that doesn't mean anything if the way that you bring your TWAPs across chains is using a multisig or an oracle to begin with. So this is a way to access that data on any other chain without actually giving up the core properties, the core benefits of the TWAPs to begin with. FujiDAO is building a lending aggregator. So they're building on top of Aave and other lending protocols. And the core use case that they want to enable is lend on any chain, borrow on any other chain. Similarly, NFT Hashi, bridging NFTs across chains, and Gnosis Zodiac, cross-chain DAO governance and tooling. There's one more really interesting use case that I'd like to touch on here, which is like one of the key things that this cross-chain world creates is building bridges, building kind of connections to ecosystems and projects that are not necessarily like EVM compatible or not necessarily even blockchains. So for instance, you can build a bridge to Arweave or Filecoin. And what that means is you can basically access storage directly from within a smart contract on Ethereum. The storage that exists is actually owned by that contract. It's not being owned by somebody else with, it's not like an IPFS hash where you have, you post some data to IPFS and then store the hash in an NFT contract. Instead, that contract is natively able to store and access data directly from within itself. Similarly, you can do run compute from within a contract using Nexus. You could do video transcoding using LivePeer or even access video data from within a smart contract. And I think the really important thing that this enables is that it allows Ethereum to kind of act as a motherboard. Right? You can plug into other kinds of resources on other chains or other ecosystems that allow you to build more expressive applications. Applications that go beyond just like relatively simple DeFi apps or NFTs or some of the basic things that we've seen so far, and go towards what basically looks more like generalized decentralized compute. Thank you for listening to my talk. My name is Arjun. If you'd like to learn more about Connext, these are a bunch of resources. And if you'd like to contact me or learn more about me, that's my handle. It's the same handle everywhere. I'm very doxed. Cool. Thank you so much. Appreciate it.